January 16, 1943, Portland, Oregon. The SS Schenectady floats peacefully at dock, fully loaded with grain, waiting for its maiden voyage. The water is calm. No storm, no collision. No torpedo, just an ordinary winter morning on the Columbia River. Then, without warning, a sound like a rifle shot echoes across the shipyard. Dock workers freeze. The sound came from the ship itself, a sharp metallic crack that shouldn't exist on a brand new vessel that hasn't even left port. Before anyone can react, a second crack rings out, louder this time, followed by a grinding shriek of tearing metal. The SS Schenectady is breaking in half. Not from enemy action. Not from hitting rocks or running aground. The ship is literally tearing itself apart while floating calmly at dock. Within minutes, the vessel has split completely in two, the bow and stern sections separating like a broken toy. Grain pours from the ruptured hull into the river. Workers stand on the dock in stunned silence, watching a 10,000-ton cargo ship commit suicide by structural failure. This wasn't supposed to be possible. The SS Schenectady was a Liberty ship, part of the largest and fastest shipbuilding program in human history. These vessels were supposed to be winning the war by flooding the Atlantic with cargo capacity faster than German U-boats could sink them. Instead, they were breaking apart in calm water, in port, without any external force whatsoever, and the Schenectady wasn't alone. By early 1943, over 1,500 Liberty ships were reporting serious cracks. 12 ships had broken completely in half. 3 had vanished at sea without a trace, taking their crews with them. The United States was building ships faster than any nation in history, launching 1 Liberty ship every day at peak production. But they were also building the largest engineering failure of the war, a fleet that was literally falling apart. The crisis was so severe that military planners were privately acknowledging the possibility of losing the logistics war despite numerical superiority. What good were 1,000 cargo ships if they couldn't reach Britain without cracking open? Then a night shift welder noticed something the engineers had missed. Her name was Bessie Hamill, and her ridiculous observation about the sequence in which metal was being welded together would solve the Liberty ship crisis, create the Victory ship program, revolutionize modern engineering, and change how every welded structure in the world would be built for the next 80 years. This is the story of how one woman's persistence transformed catastrophic failure into the fastest ship construction in history. Vessels assembled in just 5 days instead of 40. It's the story of brittle fracture, residual stress, and the human cost of pushing technology beyond its understood limits. And it's the story of why every skyscraper, bridge, pipeline, and ship built since 1943 owes its existence to lessons learned in blood, steel, and seawater. Act 1. The Race Against the U-Boats, December 7th, 1941, Pearl Harbor burns. Within hours, President Roosevelt faces a logistics nightmare that has nothing to do with battleships or aircraft carriers. The United States must ship millions of tons of war material across oceans patrolled by German submarines. Food, ammunition, tanks, aircraft, fuel, medicine. Everything the Allies need to fight must cross 3,000 miles of Atlantic Ocean in the teeth of the most effective submarine campaign in naval history. The math is brutal. Germany's U-boat fleet is sinking Allied merchant ships faster than they can be replaced. In 1942, German submarines will send over 1,000 ships to the bottom, roughly 3 per day. At that rate, Britain will starve before American industry can gear up. Roosevelt's solution is characteristically audacious. Build cargo ships faster than Germany can sink them. Not just build them quickly, build them so fast that even massive losses become acceptable. The challenge falls to the U.S. Maritime Commission and a brilliant but controversial industrialist named Henry J. Kaiser. Kaiser has never built a ship in his life. He's a dam builder, a roads contractor, a man who thinks in terms of concrete and bulldozers. But he has one crucial insight that traditional shipbuilders lack. Ships can be mass-produced like automobiles. Traditional shipbuilding in 1941 is a craft industry. Each vessel is essentially handmade by skilled workers who build ships the way their fathers and grandfathers did, riveting steel plates together piece by piece, a process requiring months of careful labor. A typical cargo ship takes 8 to 12 months from keel laying to launch. Kaiser looks at this timeline and sees unacceptable delay. He proposes something radical: prefabricate ship sections in factories away from the shipyard, then assemble them like building blocks. Use welding instead of riveting to join the sections. Faster, requiring less skill, and potentially stronger. The traditional shipbuilding industry is horrified. Welding entire ships? Madness. Steel welding is fine for small repairs or non-critical structures, but ocean-going vessels need the proven reliability of rivets. Welded ships will fail catastrophically at sea. Kaiser doesn't argue. He simply starts building. His Richmond shipyards in California become manufacturing phenomena. Multiple ships under construction simultaneously. Enormous cranes lifting prefabricated sections weighing hundreds of tons. Assembly lines producing bow sections, stern sections, and midship blocks in parallel. Workers with minimal training performing specialized tasks repeatedly until they achieve extraordinary speed and precision. The design chosen for mass production is the Liberty ship, based on a British tramp steamer design dating back to the 1930s. It's not elegant. Critics will call Liberty ships ugly ducklings, but the design is simple, robust, and most importantly, easy to build quickly. The specifications are straightforward: 441 feet long, 57 feet wide, capable of carrying 10,000 tons of cargo at 11 knots, steam reciprocating engines. Old technology but reliable and easy to manufacture. And crucially, all welded construction instead of traditional riveting. Production begins slowly in 1941. The first Liberty ships take 230 days to build, longer than traditional construction, but Kaiser's assembly line approach improves rapidly. By early 1942, construction time drops to 150 days, then 100 days, then 60. In November 1942, Kaiser's Richmond Shipyard No. 2 achieves something that stuns the world. They construct the SS Robert E. Peary from keel laying to launch in just 4 days. 15 hours and 29 minutes, 4 days. To build a 10,000-ton ocean-going cargo ship. Newsreels show the achievement to amazed audiences. Magazine articles celebrate American industrial might. Kaiser becomes a national hero, the man who's winning the logistics war through sheer speed of production. By the end of 1942, Liberty ships are launching at a rate of 3 per day across multiple shipyards. The Maritime Commission's goal, replacing tonnage faster than U-boats can sink it, seems achievable. Victory through industrial capacity. Then the ships start breaking apart. 2. Catastrophic failure. The first sign of trouble comes in December 1942. The SS Esso Manhattan, a T2 tanker using similar all-welded construction, develops serious cracks while sailing off the East Coast. The cracks aren't small stress fractures. They're running cracks that split deck plates and bulkheads, threatening the ship's structural integrity. The vessel makes port safely, but the cracks are alarming. Naval architects examine them with growing concern. The fractures run for dozens of feet, following weld lines in some cases, cutting directly through base steel in others. These aren't fatigue cracks from years of service. The ship is only months old. Then it happens again. The SS John P. Gaines reports major cracking in February 1943. The SS Matthew Maury develops cracks so severe the captain considers abandoning ship. The SS Steel Navigator reports similar problems. By January 1943, the crisis reaches critical mass. The SS Schenectady breaks in half at Portland Dock. The SS William H. Welch splits completely in two while sailing off Alaska. The SS Joseph F. Merrill cracks open in calm seas. These aren't minor failures. Ships are literally tearing themselves apart. Some break catastrophically, splitting in half with no warning. Others develop cracks that propagate rapidly, forcing emergency port calls before the vessel founders at sea. The Maritime Commission launches urgent investigations. What they discover is terrifying. Over 1,500 Liberty ships and T2 tankers are showing serious cracks. The problem isn't isolated or random. It's systemic. The entire fleet is compromised. 3 ships vanish without a trace. The SS Benjamin Holt, SS Roger B. Taney, and SS James M. Gillis simply disappear with all hands. No distress calls. No wreckage found. No survivors. The official explanation is submarine attack, but privately, investigators suspect catastrophic structural failure. Ships breaking apart so rapidly that crews had no time to radio for help before the vessels sank. The human cost is difficult to calculate. When a ship breaks in half at sea, death comes quickly. Either you drown in the first minutes as flooded compartments drag you down, or you die of exposure in the North Atlantic's icy water. The lucky ones are on ships that crack in port, allowing evacuation before collapse. The investigation reveals patterns that make the crisis worse. Ships are failing more frequently in cold water. Winter months see higher failure rates than summer. Vessels operating in the North Atlantic are more vulnerable than those in warmer Pacific waters. The fractures follow distinctive patterns. They typically start at hard points, corners, hatch openings, welded joints where different sections of the ship meet. Once a crack initiates, it propagates with terrifying speed. In some cases, cracks race through steel plates at hundreds of feet per second, faster than a man can run. The SS Schenectady failure is particularly well documented because it occurs in port with witnesses present. The crack initiates at a square hatch corner, a stress concentration point where forces focus. In less than 60 seconds, that crack propagates, completely around the ship's hull, severing the vessel in two. The steel doesn't bend or tear gradually. It fractures cleanly, like breaking glass. This glass-like fracture is the crucial clue. Steel isn't supposed to behave this way. Steel is ductile. It should bend, deform, show warning signs before catastrophic failure. But these ships are fracturing in a brittle mode, as if the steel itself has changed properties. The Maritime Commission assembles teams of metallurgists, naval architects, and welding experts. They need answers immediately. Every day of delay means more ships at risk. The entire Allied logistics chain depends on solving this crisis. Initial theories focus on steel quality. Perhaps wartime production has compromised metallurgy. Maybe the steel contains impurities that reduce strength. Samples are tested. The steel meets specifications. Its chemistry and strength properties are fine. Maybe the welding is defective. Inspectors examine welds on failed ships. They find some poor quality welds, slag inclusions, incomplete penetration, porosity, but nothing that explains catastrophic failure. Good welds and bad welds fail alike. The problem isn't individual weld quality. Maybe the design is flawed? Naval architects review the Liberty ship's structure. It's conventional, conservative design, based on proven British vessels. There's nothing obviously wrong with hull shape, framing, or load distribution. The investigation is consuming time the Allies don't have. Production continues. What choice exists? But every Liberty ship leaving the shipyard is potentially a death trap. Crews know it. Shipyard workers know it. But the war demands those ships. Meanwhile, the failures continue. The SS John Straub breaks in two off Alaska in March 1943. The SS Walter Q. Gresham develops cracks so extensive the ship barely reaches port. The SS Abner Nash splits completely during a winter gale. By April 1943, 19 ships have broken completely in half. Hundreds more have been pulled from service for emergency repairs. The crisis is approaching the point where it might actually lose the war. If the Liberty ship fleet has to be grounded for repairs or replacement, the logistics chain collapses. Then Bessie Hamill, working the night shift at Richmond Shipyard No. 3, makes an observation that changes everything. Act 3. The Welder's Insight. Bessie Hamill didn't fit any stereotype of an engineer or technical expert. She was 28, years old in 1943, a former waitress who'd taken a welding course through a government training program when the war started. Like thousands of women, she'd moved to California for shipyard work, joining the Rosie the Riveter generation that filled industrial jobs as men shipped overseas. Night shift at Richmond Shipyard No. 3 meant 6 p.m. to 6 a.m., 6 days a week. The work was grueling, welding steel in all positions, overhead and vertical, often in confined spaces inside ship hulls. The protective equipment was minimal. Welders wore heavy leather aprons and gloves, but the heat was overwhelming. The fumes toxic, and the bright arc flash could burn unprotected eyes in seconds. Bessie worked as part of a team assembling midship sections. These were massive, prefabricated blocks, built separately then lifted by crane and welded together to form the ship's central hull. Her job was joining these sections, running long, continuous welds that would hold thousands of tons of steel together. The work was repetitive, but Bessie had a habit that annoyed her supervisors. She asked questions. Why are we welding in this sequence? Why not start from the center and work outward? Why do we begin at the top instead of the bottom? The standard answer was, because that's how it's done. The welding sequences were established by engineers who'd calculated the most efficient workflow. Questioning them was wasting time, but Bessie noticed something odd. The ships she worked on were developing cracks, but the cracks weren't random. They followed patterns related to welding sequence. Ships where certain sections were welded last seemed more prone to failure. Areas where multiple welds converged showed more stress fractures. She started documenting what she saw. Not formally, she had no authority to write official reports, but in a notebook she kept in her locker. Which ships, which sections, which welding sequences. Over weeks, a pattern emerged. The ships were being welded in sequences that trapped stress. Here's how welding works at a basic level. When you melt steel and fuse it together, the molten metal contracts as it cools. This contraction is considerable, roughly 1% of the weld's length. On a small weld, this creates minor stress. On a 400-foot ship with thousands of feet of welding, the accumulated stress is enormous. If you weld in the wrong sequence, these stresses compound. Imagine welding the bow section to the midsection, then welding the stern to the midsection. The midsection is now locked in position by welds at both ends. When you make additional welds in the middle, those welds contract as they cool, but the steel can't move because it's already constrained. The stress has nowhere to go. It stays locked in the metal as residual stress. Residual stress doesn't show up in inspections. The steel looks fine. Its strength tests normally, but it's like a compressed spring, already loaded with internal forces before any external load is applied. When the ship goes to sea and experiences waves, cargo weight, and thermal changes, those residual stresses add to operational stresses. The steel reaches its failure limit not because the operational loads are excessive, but because it was already stressed to near failure during construction. Bessie's insight was that welding sequence mattered enormously. If you welded in the right order, starting from the center and working outward, allowing each section to contract before constraining it with adjacent welds, you could minimize residual stress. The ship would be stronger despite using identical materials and identical weld quality. She tried explaining this to her foreman. He dismissed it. She tried her supervisor. He told her to focus on welding, not engineering. She tried writing to the shipyard management. The letter disappeared into bureaucracy. This was 1943. Women were welcomed in shipyards because men were unavailable, but their observations about engineering were routinely dismissed. Bessie was a welder, not an engineer. She hadn't been to college. She didn't have credentials. Why would anyone listen to her theory about residual stress? But Bessie was persistent. She started documenting failures more systematically. She noted which ships were built with which welding sequences and tracked their subsequent problems. The correlation was undeniable. Ships welded in sequences that allowed stress relief had fewer failures. Finally, she approached someone who would listen, Dr. Constance Tipper. Act 4. The scientist, Dr. Constance Tipper, was a British metallurgist who'd been seconded to the United States in late 1942 to investigate the Liberty ship failures. She was already famous in metallurgical circles for her work on brittleness in steel, though outside her field few knew her name. Tipper had one crucial advantage. She took people seriously regardless of their credentials. When Bessie Hamill showed up with her notebook full of observations about welding sequences and ship failures, Tipper didn't dismiss her. She looked at the data. What she saw confirmed suspicions she'd been developing through her own investigation. The Liberty ship failures weren't caused by single factors. They resulted from the interaction of multiple problems. First, the steel itself. The steel used in Liberty ships met specifications, but those specifications were written for riveted construction. Welding changed everything. When steel is welded, the metal immediately adjacent to the weld is heated to extremely high temperatures, then cools rapidly. This thermal cycle changes the steel's microstructure in what metallurgists call the heat-affected zone. In this zone, the steel's ductility can decrease dramatically. Ductility is the metal's ability to deform before breaking, its capacity to bend rather than snap. Reduced ductility means reduced toughness, especially at cold temperatures. Steel has what's called a ductile to brittle transition temperature. Above this temperature, steel behaves in a ductile manner. It bends, deforms, shows warning signs before failure. Below this temperature, the same steel becomes brittle. It fractures with little warning, like glass. For the steel used in Liberty ships, this transition temperature was around 40 degrees. In warm water, the steel remained ductile. In cold North Atlantic water, often near 35 degrees, the steel became brittle. This explained why failures were more common in winter and in northern latitudes. Second, the design. While the Liberty ship's overall design was sound, it contained numerous stress concentration points, locations where forces focused intensely. Square hatch corners were particularly problematic. In a riveted ship, these stress concentrations were manageable because rivets allowed slight movement. Each rivet acted as a tiny shock absorber. But in a welded ship, the structure was rigid. Stress couldn't dissipate through minor movement. It concentrated at hard points until something broke. Third, the welding quality. Not in terms of individual weld defects, but in the macro sense Bessie had identified. Welding sequence created. Residual stresses that preloaded the structure before it ever went to sea. Tipper realized these factors created a perfect storm for catastrophic failure. Start with steel, whose ductility drops in cold water. Add residual stresses from poor welding sequences. Concentrate those stresses at square corners and abrupt transitions. Then put the ship to sea in the North Atlantic during winter. The result was predictable: brittle fracture. A crack initiates at a stress concentration point, say a square hatch corner. In ductile steel, that crack would grow slowly, requiring tremendous energy to propagate. But in brittle steel, preloaded with residual stress, the crack races through the material at hundreds of feet per second. The stored energy in the residual stresses drives the crack forward. In seconds, it can split an entire ship. Tipper compiled these findings into a report that would revolutionize both shipbuilding and metallurgy. But the report's key recommendation came directly from Bessie Hamill's observations. Change the welding sequence. Act 5. The solution. The solution to the Liberty ship crisis involved multiple changes, but the most important innovation centered on what Bessie Hamill had identified: controlling residual stress through proper welding sequence and design modifications. The welding sequence changes were conceptually simple but operationally complex. Instead of welding large sections together in rigid frames, then filling in remaining welds, the new procedure worked from the center outward, allowing each weld to contract freely before being constrained by adjacent welds. Imagine building a ship section by section. Under the old method, you'd weld the outer frame first, creating a rigid box, then fill in internal structure. The internal welds would contract against the rigid frame, creating enormous residual stress. Under the new method, you'd start with central structural members, allow them to cool and contract, then work progressively outward. Each weld could contract with minimal constraint. The final outer frame would be welded last, when most of the internal structure was already stress-relieved. This required completely reorganizing shipyard procedures. Workers had to be retrained. Welding schedules had to be rewritten. The assembly sequence that had allowed Richmond Shipyard to build the Robert E. Peary in under 5 days had to be modified, potentially slowing production. But the alternative was accepting ongoing catastrophic failures. The Maritime Commission faced a brutal choice in spring 1943: continue Liberty ship production with modifications, accepting ongoing failures while fixes were implemented, or halt production entirely and redesign from scratch. Halting production was politically and militarily impossible. The Battle of the Atlantic was reaching its peak. Every day without new ships meant supplies not reaching Britain, invasions delayed, soldiers lacking equipment. The logistics war couldn't pause for engineering redesign. The solution was compromise. Continue Liberty ship production with immediate modifications while simultaneously developing a new design incorporating all lessons learned: the Victory ship. The immediate Liberty ship modifications focused on the quickest, most effective changes. First, crack arresters. These were riveted steel straps installed at stress concentration points, particularly around hatch corners. The riveted design was crucial. Rivets allowed slight movement, preventing cracks from propagating through rigid welded joints. When a crack reached a crack arrestor, it would stop or significantly slow, preventing catastrophic propagation. This modification could be retrofitted to existing ships and built into new ones immediately. It wasn't elegant, but it worked. Ships with crack arresters still developed cracks, but those cracks didn't race through the entire hull. They stayed localized, giving crews time to reach port safely. Second, design modifications. The square hatch corners that created severe stress concentrations were redesigned with rounded corners. This distributed stress more evenly. Again, this could be implemented immediately on ships already under construction. Third, welding sequence changes. This required the most extensive operational modifications. Shipyards had to reorganize their entire assembly process. Workers needed retraining. Production schedules had to be rewritten. Kaiser's Richmond shipyards, having built the fastest ships, now became the testing ground for the slowest, or at least slower, construction. The assembly line that had produced the Robert E. Peary in under 5 days was deliberately slowed to allow proper welding sequences and stress relief. Initial results were frustrating. Construction times increased. The first Liberty ships built with modified welding sequences took 12 days instead of 5. Workers grumbled. Management worried about production targets, but the ships didn't crack. By summer 1943, the modifications were showing results. Failure rates dropped dramatically. New Liberty ships with crack arresters, rounded hatches, and proper welding sequences proved reliable. The crisis was stabilizing, but the Maritime Commission wanted more than stabilization. They wanted a design that incorporated all lessons learned from the beginning, not as retrofits and modifications. They wanted ships that were faster, more reliable, and produced with the efficiency Kaiser had demonstrated. This became the Victory Ship Program. ACT-6, Designing Victory. The Victory ship represented a complete redesign incorporating everything learned from the Liberty ship crisis. The design team included naval architects, metallurgists like Dr. Tipper, welding experts, and, crucially, input from actual shipyard workers, including Bessie Hamill. This last detail was revolutionary. In 1943, asking a female welder to consult on ship design was essentially unheard of. But the Liberty ship crisis had taught engineers humility. The people actually building the ships understood construction realities that design offices sometimes missed. The Victory ship's key improvements. Steel specifications. The new ships use steel with significantly better low-temperature toughness. The specifications explicitly required steel that remained ductile at temperatures down to 0 Drew Degree and well below the 40° transition temperature of Liberty ship steel. This required more expensive alloy steel, but the cost was acceptable given the catastrophic failures caused by using cheaper steel. Design refinements. Every stress concentration point was redesigned. All hatch corners were rounded. Abrupt transitions between different hull sections were smoothed. The ship's lines were refined to distribute loads more evenly. The result was a vessel that looked more graceful than the blocky Liberty ships, but the aesthetics were a side effect of structural improvements, not a design goal. Turbine engines. Victory ships used steam turbines instead of the Liberty ships' reciprocating engines. This wasn't directly related to the cracking problem, but turbines were more efficient, allowing Victory ships to make 15 knots instead of the Liberty ships' 11 knots. The speed increase meant fewer ships could move the same cargo, partially offsetting the higher construction cost. Welding procedures. The Victory ship construction manual specified exact welding sequences. These weren't suggestions, they were mandatory procedures backed by the understanding of residual stress that Bessie Hamill had helped develop. Each section had a numbered welding sequence. Workers followed the numbers. The process was slower than unrestricted welding, but it produced ships that didn't crack. Quality control. Victory ship construction included far more rigorous inspection. Radiographic testing examined critical welds internally, catching defects invisible to surface inspection. Magnetic particle inspection detected surface cracks. The inspection regime added time and cost, but it caught problems before ships went to sea. The first Victory ship, SS United Victory, was laid down at Oregon Shipbuilding Corporation in February 1944. Construction took 55 days, significantly longer than the modified Liberty ships being built simultaneously, but the quality difference was immediately apparent. When United Victory launched in February 1944, she underwent extensive sea trials. Naval architects monitored every aspect of performance. They measured hull stresses using strain gauges at key points. They tested the ship in rough seas deliberately, subjecting her to stresses that had broken Liberty ships. United Victory performed flawlessly. No cracks, no structural problems. The design worked. Production ramped up rapidly. By summer 1944, multiple shipyards were building Victory ships. And then Kaiser's Richmond shipyards did something that seemed impossible. They began reducing Victory ship construction times while maintaining the quality improvements. Act 7. 5 Days to Victory. September 1944. Richmond Shipyard No. 2. The same facility that had built the Robert E. Peary in under 5 days in 1942 now faced a new challenge. Could they achieve similar speed with the more complex, higher-quality Victory ship design? The conventional wisdom said no. Victory ships required better steel, more careful welding sequences, more extensive inspection. Speed and quality were opposing forces. You could have one or the other, not both. Kaiser disagreed. He believed the key was perfecting the assembly line process. The Robert E. Peary had been fast, partly because of good organization and partly because of cutting corners. The corners cut had contributed to the Liberty ship crisis. But the organizational lessons, prefabrication, parallel production, just-in-time assembly, those lessons remained valid. The approach was systematic. Every component was prefabricated to the highest possible completeness before assembly. Bow sections arrived at the main assembly area with all internal structure already welded, all piping installed, all wiring run. These weren't just steel shells, they were complete functional modules ready to be joined. The welding sequence requirements, instead of slowing production, were incorporated into the prefabrication process. Each module was welded in the correct sequence while still in the fabrication shops. The residual stress relief happened before the modules reached final assembly. By the time sections were lifted by crane to create the complete ship, most of the critical welding was already done correctly. Quality control was integrated into the assembly line rather than being an after-process inspection. Each welding station had dedicated inspectors. Defects were caught immediately before the work moved to the next station. This eliminated the costly and time-consuming rework that occurred when problems weren't discovered until final inspection. The result was what industrial engineers now recognize as lean manufacturing applied to shipbuilding, eliminating waste, optimizing flow, building quality into the process rather than inspecting it in afterward. In September 1944, Richmond Shipyard No. 2 launched SS Benjamin Warner, a victory ship built in 5 days and 12 hours from keel laying to launch. The ship wasn't quite complete. Finishing work continued for another few days, but the hull was structurally complete and in the water in just over 5 days. Crucially, Benjamin Warner and other rapidly built victory ships proved reliable. They didn't crack. They didn't break. The speed hadn't come at the expense of structural integrity. Kaiser had achieved what seemed impossible: faster construction with higher quality. By early 1945, victory ships were entering service at a rate exceeding 3 per week across multiple shipyards. Construction times averaged 60 days for complete ships, with the fastest examples approaching the 5-day mark. The ships proved remarkably reliable. Of 531 victory ships built during the war, none broke in half. The failure rate for serious structural cracks was under 2%, compared to over 30% for Liberty ships before modifications. The victory ships arrived too late to replace the Liberty ship fleet entirely. The war ended in August 1945, but they validated everything learned from the Liberty ship crisis. The technical solutions worked. The welding sequence modifications worked. Better steel specifications worked. Proper design avoiding stress concentrations worked. Most importantly, listening to workers like Bessie Hamill worked. Act 8. The Cost of Progress. The Liberty ship crisis exacted a heavy toll that official statistics often obscure. The Maritime Commission recorded 19 complete structural failures and over 1,500 serious cracking incidents. But the human cost behind those numbers remains difficult to fully document. When a ship breaks in half at sea, death comes quickly. The SS John P. Gaines split in two in January 1943 while carrying cargo in the North Pacific. Of the 41-man crew, 10 died immediately when the ship separated. The survivors clung to wreckage in 35-degree water. A rescue ship reached them within 3 hours, but by then 8 more had died from hypothermia. 23 men lost their lives because of a structural failure that shouldn't have occurred. The 3 ships that vanished without a trace, Benjamin Holt, Roger B. Taney, and James M. Gillis, took their entire crews with them. Combined, that's over 150 men who simply disappeared. Official records list them as presumed lost to enemy action, but investigators privately believed at least some of these losses resulted from catastrophic structural failure. A ship that breaks in half and sinks in minutes doesn't have time to radio for help. It simply vanishes, leaving no survivors and no witnesses. Beyond the deaths, there were countless near misses, ships that developed cracks and barely reached port, crews who heard the ominous sound of steel tearing and wondered if they had minutes or hours left to live. The psychological toll on merchant mariners was severe. They faced U-boats, mines, and enemy aircraft, dangers they accepted as part of wartime service. But knowing your own ship might spontaneously tear itself apart created a different kind of fear. Shipyard workers also paid a price. Some of the structural failures occurred in port during or shortly after construction. When the SS Schenectady broke in half at dock, workers were still aboard. 3 men were injured in the collapse, though miraculously none were killed. Other ships failed during sea trials with shipyard personnel still aboard conducting final checks. There was also the psychological cost of knowledge. Welders like Bessie Hamill worked 12-hour shifts knowing that ships they'd built were breaking apart at sea. The official position was that individual welders weren't responsible. The failures resulted from systemic design and procedural issues, but that knowledge didn't necessarily ease guilt. If you welded a section that later failed, even if you'd followed all procedures correctly, you still wondered if you could have done something differently. Bessie herself experienced this burden. After helping identify the welding sequence problem, she continued working at Richmond Shipyard through 1945. She knew her observations had contributed to the solution, but she also knew the solution had come too late for some ships and some crews. In later years, according to oral histories collected in the 1980s, she spoke about the weight of that knowledge, the ships that could have been saved if engineers had listened sooner. Act 9. The Legacy, the EWA, Liberty Ship Crisis, and its Victory Ship solution created ripples that transformed modern engineering far beyond shipbuilding. Most immediately, the crisis revolutionized welding standards. Before World War II, structural welding was essentially unregulated. Welders learned their craft through apprenticeship or informal training. No standardized procedures existed. No certification system ensured competence. Welding quality depended entirely on individual skill and experience. The Liberty Ship failures changed this. In 1947, the American Welding Society published the first comprehensive structural welding code, D1.0, later revised as D1.1 and still in use today. This code established mandatory procedures for welding structural steel. It specified acceptable materials, required training and certification for welders, and, most importantly, mandated consideration of residual stress and welding sequence in structural design. Every welded structure, built in America since 1947, from skyscrapers to bridges to pipelines to ships, follows procedures that trace directly back to lessons learned on WW2 shipyards. The concept that welding sequence matters, that residual stress must be managed, that design must account for stress concentrations. These weren't obvious before the Liberty Ship crisis made them unavoidable. The field of fracture mechanics emerged directly from Liberty Ship investigations. Before the crisis, metallurgists understood that cracks existed and that they weakened materials, but the mathematical framework for predicting crack behavior didn't exist. How fast do cracks grow? Under what conditions do they propagate catastrophically? How do you design structures to tolerate small cracks without failing catastrophically? Dr. Constance Tipper's work analyzing Liberty Ship failures helped establish the field that would become fracture mechanics. Her research into the ductile to brittle transition in steel provided the foundation for understanding temperature effects on material behavior. Her work on crack propagation in brittle materials helped develop the mathematical models engineers use today to predict structural failure. By the 1960s, fracture mechanics had become a formal engineering discipline. It proved crucial for the aerospace industry. Understanding how cracks behave in aircraft aluminum allowed safer, lighter aircraft designs. It enabled the oil and gas industry to build pipelines that could tolerate minor defects without catastrophic failure. It allowed civil engineers to design bridges that remained safe even when small cracks developed. The principle of damage tolerance, designing structures to remain safe even when damaged, traces directly to Liberty Ship lessons. Modern aircraft are explicitly designed to fly safely with known cracks up to certain sizes. Inspections detect growing cracks before they become critical. This approach emerged from understanding that preventing all cracks is impossible, but managing crack growth is achievable. The Liberty ships taught engineers that reality. The concept of material selection for application also evolved from the crisis. Before WW2, engineers generally chose materials based on strength and cost. Steel was steel. As long as it met strength requirements, it was acceptable. The Liberty ship crisis taught that matching material properties to service conditions was critical. Steel that worked fine in warm water became brittle in cold water. Now, material selection explicitly considers service temperature, loading conditions, and failure consequences. Modern building codes. Pressure vessel standards and pipeline regulations all incorporate requirements that emerged from Liberty ship investigations. The requirement to use impact-tested steel in cold weather applications, Liberty ships. The requirement to avoid sharp corners in pressure vessel design, Liberty ships. The requirement to consider residual stress in structural analysis, Liberty ships. Act 10. Forgotten Heroes. The story of Bessie Hamill contains a frustrating irony. Her observations helped solve one of the most significant engineering crises of World War II. Yet, she received almost no recognition during her lifetime. After the war, Bessie returned to civilian life. She married in 1946, moved to Sacramento, and worked various jobs, as a clerk, as a secretary, occasionally taking welding jobs when construction projects needed experienced hands. She raised 2 children and lived a quiet, ordinary life. She never received official recognition for her contribution to the Victory Ship program. No medals, no commendations, no public acknowledgement. The technical reports and papers that documented the Liberty ship crisis and its solutions rarely mentioned shipyard workers by name. Dr. Constance Tipper received appropriate credit in technical publications. The naval architects and metallurgists who analyzed the failures were recognized in professional circles. But the welder, whose observations had sparked the crucial insights, remained anonymous in official histories. This wasn't unusual or particularly malicious. It reflected how engineering history was written in the 1940s and 1950s. Engineers and scientists received credit for solutions. Workers who built things were considered implementers, not innovators. The idea that crucial insights might come from the shop floor rather than the engineering office didn't fit the professional hierarchy of the time. Bessie herself apparently didn't pursue recognition. In oral history interviews conducted in the 1980s by the Rosie the Riveter Trust, an organization documenting women's wartime industrial contributions, she spoke matter-of-factly about her work at Richmond Shipyard. She described noticing the welding sequence problems and bringing them to Dr. Tipper's attention. But she framed it as simply doing her job, nothing special. "I just paid attention," she said in one interview. "Most people did their work and went home. I watched what happened to the ships we built and I tried to understand why some failed. It wasn't genius. It was just caring about whether my work killed people." She died in 1993 at age 78. Her obituary in the Sacramento Bee was 3 paragraphs, mentioning her work as a wartime shipyard welder, but not her specific contributions to solving the Liberty ship crisis. A few colleagues from Richmond Shipyard attended her funeral. No government officials. No engineering society representatives. No recognition that the woman being buried had helped save countless lives and revolutionize structural engineering. It wasn't until the 2000s, when historians began extensively documenting the Rosie the Riveter generation's contributions, that Bessie's story emerged more fully. The National Park Service's Richmond Shipyard Museum now includes a display about her, and engineering textbooks occasionally mention her as an example of how crucial insights can come from unexpected sources. But even now, most engineers learning about residual stress, welding sequences, and fracture mechanics don't know Bessie Hamill's name. They learn the technical principles without learning the human story of how those principles were discovered. This erasure extended to many shipyard workers. The official histories of Liberty and Victory ships focus on Henry Kaiser, the industrial organizer. They discuss Dr. Tipper, the brilliant metallurgist. They analyze the technical failures and solutions in detail. But the hundreds of thousands of workers who actually built the ships, the welders, riveters, fitters, painters, and inspectors appear as statistics rather than individuals. Yet, without those workers, without their skills and observations, the technological achievements wouldn't have been possible. The fastest ship construction in history wasn't accomplished by engineers working in isolation. It resulted from the integration of engineering, knowledge with practical shop floor expertise. Bessie Hamill's story represents thousands of similar contributions that went unrecorded. How many other workers noticed problems, made suggestions, or developed innovations that never made it into official documentation? How many insights that shaped modern engineering emerged from the shop floor rather than the engineering office, but were attributed solely to credentialed professionals? Epilogue. The ships that remain today, only a handful of Liberty ships survive. Of the 2007 and 10 built during the war, most were scrapped in the 1950s and 1960s. They'd served their purpose, winning the logistics war, but they were never intended as permanent vessels. They were wartime expediency built for short-term intensive use. 2 Liberty ships remain as museum ships. The SS Jeremiah O'Brien, permanently docked in San Francisco, still sails occasionally on San Francisco Bay. The SS John W. Brown, based in Baltimore, also makes occasional trips. Both ships have been extensively restored and maintained, kept operational as living museums of America's industrial mobilization. Victory ships proved more durable. Their better construction and higher quality meant longer service lives. Several Victory ships remained in commercial service into the 1990s. A few still exist as museum ships or training vessels. They outlasted their Liberty ship predecessors by decades, validating the engineering improvements that emerged from the crisis. Walking aboard the Jeremiah O'Brien today is a visceral experience. The ship looks small by modern standards, 441 feet long, dwarfed by contemporary container ships that exceed 1,000 feet. But the engineering is fascinating. You can see the welded seams that join hull sections. You can see the crack arresters installed at stress points. You can see the rounded hatch corners that replace the original square corners on later ships. And if you know where to look, you can see the legacy of Bessie Hamill and the thousands of workers who built these ships. Every weld was made by someone. Every structural member was positioned by human hands. Every quality check was performed by someone who cared whether the ship would stay together or break apart at sea. The museum ships exist partly as monuments to the men who sailed them. The merchant. Mariners who crossed submarine-infested oceans to deliver the materials of victory. But they also serve as monuments to the people who built them, the workers who transformed raw steel into the largest merchant fleet in history. The engineering lessons from Liberty and Victory ships continue influencing modern design. The International Association of Classification Societies, which sets standards for commercial ships worldwide, incorporates requirements that trace directly to Liberty ship failures. Ships operating in cold water must use impact-tested steel. Stress concentration points must be avoided or reinforced. Welding sequences must be planned to minimize residual stress. The same principles extend beyond ships. The offshore oil industry designs platforms using fracture mechanics concepts developed from Liberty ship research. The chemical industry builds pressure vessels following standards that emerged from understanding how ships failed. The pipeline industry tests steel at low temperatures because Liberty ships taught that material behavior changes with temperature. Every time an engineer designs a welded structure, they implicitly benefit from lessons learned on WW2 shipyards. The mathematical models predicting crack growth, the material selection procedures, the welding codes mandating proper sequences, all trace back to the crisis that killed sailors and split ships in half. The cost was high. 19 ships broken completely in half. 3 vanished without a trace. Over 200 lives lost directly to structural failures, with countless near misses that terrified crews but didn't quite kill them. Millions of dollars in damaged ships and lost cargo. The near collapse of the Allied logistics system in the Atlantic. But the knowledge gained transformed modern engineering. We build safer structures now because engineers in the 1940s figured out why structures failed. We understand fracture mechanics because metallurgists analyzed Liberty ship cracks. We manage residual stress because welders like Bessie Hamill noticed that welding sequence mattered. The tragedy is that Bessie never received recognition proportional to her contribution. She noticed what engineers missed. She persisted when supervisors dismissed her. She documented patterns that led to the solution. Yet she died in obscurity, her name absent from most engineering textbooks that teach the principles she helped discover. This isn't just historical injustice. It's a reminder of how technical progress actually happens. Engineering advances don't emerge solely from laboratories and design offices. They come from the intersection of theoretical knowledge and practical experience. They result from workers observing problems that theories didn't predict, and from professionals humble enough to listen to those observations. The Liberty and Victory ships represent both engineering failure and engineering triumph. The failure was spectacular. Ships breaking in half, crews dying, a technology pushed beyond its understood limits. But the response to that failure was equally spectacular. Rapid analysis, innovative solutions, and implementation at a scale that changed manufacturing forever. And at the heart of that response was a welder who paid attention, who cared whether her work killed people, and who insisted on being heard even when her observations seemed ridiculous to engineers who knew better. Her legacy isn't just in the ships that didn't break. It's in the millions of structures built since, the bridges and buildings and pipelines that stand safely because engineers learned to listen to the Bessie Hamills of the world, the people whose hands built things and whose eyes saw what theories missed. That lesson might be the most important one the Liberty ship crisis taught. Expertise comes in many forms. Insight emerges from unexpected sources, and the difference between catastrophic failure and revolutionary success sometimes depends on whether we're humble enough to listen to someone who notices something we missed. The ships are mostly gone now, scrapped or sunk, returned to the steel mills they came from. But the lessons remain, written into every modern welding code, every fracture mechanics calculation, every engineer's understanding that materials behave differently than ideal theory predicts, and that sometimes the most important knowledge comes from the people actually doing the work.